Hi, everyone. Welcome to another Seismic Academy. My name is Daniel. I've done a decent number of these by now. This one's going to be on Fourier analysis and how it relates to earthquake engineering. So just going over what we're going to talk about, we're going to talk about what a Fourier series and a Fourier transform are and what do they do. I'm going to go through why this is useful for us on our team. We're going to watch a video about what the math is behind it and how it works. And then after that, we're going to see its applications in finding our tower properties, in building some understanding of why towers respond to ground motions the way they do, and then a fun little slide about synthetic ground motions. So to start off, a Fourier series is just this idea that you can make any function you want. So whether it's a ground motion on history or, like any function of any kind, you can create it with this infinite series of sine and cosine waves. And this is similar to the idea of Taylor polynomials, which I'm pretty sure everyone learned about in first year, which is another idea that every function can be created from a summative infinite series of polynomials as long as you change the different coefficients. And then in our case, for the Fourier series, we're going to use sine waves at different amplitudes and of different frequencies. So for example, sine 3x plus 5 cos 4x would give us a different function. And then the frequencies that we use to build up this function is kind of what we would call the function's frequency content. And so just a quick example, as a sawtooth wave, so you can see, these are straight lines. They look pretty hard to make with sine and cosine. And if I leave the presentation and I go, so you can see here we just have a sine wave, and I'm going to add a couple more. So I'm going to add up all of these individual sine waves together. You can see the functions, sine x, sine 2x divided by 2, sine 3x divided by 3, and so on. I'm just going to get rid of these. And so as I add, the first one plus the second one, it's a little different. And then as I keep adding them, it looks more and more like that sawtooth wave. And in fact, I've set up a little series here. So you can see right now these are both the same because this sum here goes up to 6. And then once I crank this up even higher, it's going to resemble more and more that sawtooth function. So by the time I get to 1,000, like you can see it's very closely approximating. And eventually once this reaches infinity, it literally will be that sawtooth function. So that's just one example of how we can build things up using just sine waves. But of course, you can do this with sine and cosine, same thing. So back to the presentation. So that's a Fourier series. A Fourier transform, what it does is, knowing that we can use up these sine and cos waves to build up a function, the transform is what lets us go and seeing from which frequencies we used to build up the function that we have. So as Wikipedia says, it decomposes a function into its constituent frequencies. So for example, in the image here, you can see the dark blue line is a sum of two sine waves. And that Fourier transform lets us see, this frequency and this frequency were used to build up that original sine wave, or that complex wave. So why, this is pretty neat. Why do we care? Just throwing back to the very first seismic category, remember that this is kind of analogous to how a building can be decomposed. So, the way a building deforms is pretty complicated, but what's cool is that we can decompose it into the different ways it can move, what are called its modes. And then each mode has a different shape, but also a different frequency. And once we know the frequency of each mode, we can approximate each mode as a single degree of freedom system, which you can see on the bottom as just a pendulum that goes back and forth with a certain frequency. And then by finding the response of each of those systems for a given ground motion and then summing them up using some statistical method, we can approximate the response of our tower in an earthquake. So knowing that the tower, the building's earthquake response is dictated by these different frequencies, it's useful to know these frequencies, ahead of time. So you can see here an example of, how a really complicated shape is made up of a bunch of different mode shapes with different, multipliers. The first mode going to be dominant, but then, the other mode still matters. So here's an example, by the way, of those different mode shapes and what they look like. So that's the single degree of freedom and multi-degree of freedom videos that I put in the chat, which we can watch right now. So I don't know how well it's going to load in the presentation, so just watch it. You can open up YouTube on the side and watch. This is actually, interestingly enough, done by Professor Kwan, who's now here at U of T. Probably taught you guys EngMath, or will teach you guys EngMath, when back in Missouri State. So you can see here 3 different towers, basically. The only difference being their period. So they all have the same math, just they're different lengths, and the taller it is, the more flexible it is. And so what's going to happen is this, shake table, which interestingly enough is the same shake table we have at U of T, I'm pretty sure, is going to slowly increase how fast it's going back and forth. And you're going to see it's going to hit each one of these different models' fundamental frequency, and it's going to go into resonance. You can see it. So for me, it's close to the first one now. But what's also interesting is that, just because an object isn't in resonance doesn't mean it's not shaking. So even when, one of the towers is clearly in resonance, the other towers are still shaking, which goes to show that, towers shake from all different input frequencies, not just the resonant ones. Okay, so I'll give you guys a couple minutes to watch that and see how those different single degree of freedom systems react. And the reason they're single degree freedom system is that really they can only move in one way. A degree of freedom just means, there's only one possible motion, and that's back and forth. Like this isn't really going to rotate. It's too stiff to really rotate. So yeah, I'll give you guys a couple minutes to watch that, and then we can reconvene when you're done. I guess you could also watch it on like 1.5 or 2 times speed. There's no narration or anything. Yeah, so that's an example of different single degree freedom systems, where the only thing different is just their period, essentially, reacting in different ways to different frequencies. Okay, I think I'll stop it right there. Okay, cool, everyone's ready. All right, so now a similar idea, but this time we have a multiple degree freedom system. You can see there's 3 different, so Osang Huang. So we can see 3 different masses, which means there's going to be a couple different mode shapes that this building can have. And as we go through and do the same SINE sweep, so as we go through different frequencies of the SINE excitation, you'll see different mode shapes happening at different frequencies, which is going to be pretty interesting. So this is the fundamental mode shape. Usually the lowest frequency one is always going to be the most dominant one. Yeah, so that just happened at 4.35 hertz, and then it passed, and now we're going to get to the next mode shape. And then as these mode shapes become higher and higher frequencies, just to recap the first lecture, their shapes are going to get more and more complicated in terms of how many modes you have, or how many nodes you have, which is places where there's very little rotation, and how many peaks you have. And you can see we're getting closer and closer to a mode shape where the one in the middle doesn't move very much, but these 2 on the top and bottom move quite a bit. So you can really see it now. It just hit its fundamental frequency. It's a second mode frequency, where the mode shape is kind of like an S. Yeah, and then theoretically you can keep going, and you'd get a couple more mode shapes, but I think because of the shake table, they don't want to push it that far, I guess. Cool. All right, and so now kind of the math behind the Fourier transform. I'm going to reference a 3 Blue 1 Brown video, who's an excellent math YouTuber. And I sent the link in the chat so you can watch that. This video is 20 minutes long, but it is quite interesting and quite well done. I think what I'm going to do is I'll have it play on my screen, but if you want to watch it on your own, you can use the YouTube video and like mute the Teams call, and then we'll be done, I guess, in 20 minutes from now. Okay, so hopefully that video was pretty cool. The next video actually about the uncertainty principle is really interesting as well, but also has some cool concepts that do come up for us as well. I'm not going to make us watch that, but if you do want to watch it on your own, it is I do recommend it. It does add a bit more context and like theoretical framework for what we do as well. It also has a video on the Fourier series, which is also similarly interesting. And just as a quick example on Desmos of the Fourier transform, you can see here, cos 5x plus cos 3x pi. And then when you take the Fourier transform, you can see those peaks at 3 and 5. And then if I was to, as this gets larger and larger, this, I don't know how well it'll load because this is pretty slow, but this will get more and more refined. So yeah, I put a link to this as well, although this calculator is quite slow if you start adding stuff or changing things to it. Okay, so that's all I had for that part. Okay, so that was pretty cool. Hopefully now you guys have a good sense of what the Fourier transform is and kind of how it works. And we can go on to learning how we're going to use this for the tower. So one thing that we also talked about in the first Seismic Academy was the idea of free arbitration. So if we were to fix the tower at the base and then excite it, so like pushing on the top and then letting it go, we would get this free arbitration graph on the right. And by finding the distance between those peaks, we can find out its period. But what we can also do is look at the Fourier transform of this graph and see what the dominant frequencies are, because obviously the tower's fundamental frequency is what's dominating this graph. So if I go out and I go to trusty seismosignal, so here is the, don't look at the two bottom graphs, those are the reason they go down is some weird artifact of integration. But if you look at the top graph, that's acceleration in G's of 3 different free arbitrations that we did for the 2018 Vancouver tower. I don't remember, but this is the long side, or sorry, this could be either the 2018 ground motion or the 2018 tower or the 2019 tower. I don't remember if it's the long side or the short side, but regardless, 3 really pretty nice free arbitrations. And when we look at the Fourier transform of this, on the bottom left here, you can see that right at the peak, this is going to be the same number that we calculate as the distance between these peaks. And you can see frequency of 5.2 and period of 0.1916. It corresponds to this peak right here. That's pretty cool. However, what you should note, so this is a really nice free arbitration, but for example, this year we had a really not nice free arbitration where the tower, what would happen is we start pushing it and it would shake first in the x direction that we pushed it, and then it would slowly transition to the y direction. So if I load that up, so this is, for example, the x direction. You can see this is not quite as nice of a curve. There's these like little weird interferences, and this is because of the torsional asymmetry of the tower. It's the mode shape isn't quite as nice. It's not like a simple cantilever. It's rotating. But even then, here you can see, once you take the Fourier transform on the bottom left, you get this really nice peak right at 0.14787 seconds period, or 6.76 hertz. And if you look at we recorded both the x and the y acceleration, and if you look at the y, you can see, so the peak started at the x and then it transitioned into the y before transitioning to the x again. It's kind of doing this like weird tipping in and out thing. But even then, the period is almost I'm pretty sure the exact same for both the x and the y of 0.14787. So yeah, this makes finding the period of the tower a lot easier when we're using free arbitration as opposed to just calculating the difference, because there's also a lot of issues with like the accelerometer isn't that precise on our phones, so it's hard to do the easier math. So yeah, this is one nice property. So yeah, this is really easy, simple, and fast. We can just do this on our own with just our phone accelerometers. But it works better when there's just one dominant mode shape with a simple mode shape, like a cantilever for a rectangular tower. For this year, we tried doing a white noise test. White noise being what Wikipedia says is random signal containing equal intensity at different frequencies. And now that you have an idea of what the Fourier transform does, what you can imagine is if you take the Fourier transform of that, then it's going to be a pretty flat function because each frequency is being sampled at an equal rate. So we were able to input that into the shake table, and that'll let us excite the tower at a bunch of different frequencies to see which ones go into resonance. And then based on the tower vibrating at a resonant frequency, we can put an accelerometer on the tower, measure it, and once we take the fast Fourier transform, we should be able to see when it hits resonance, those frequencies being more prominent. So if I go to the white noise test over here, so you can see this this function looks pretty random to me. I don't see any patterns in it. And when we take the fast Fourier transform, this is a little bit messier, but we still have the first peak here at 0.14895, which is really close to the peaks that we got from the free vibration. There's going to be other peaks, so there's like this peak, which is at, it seems like 50 hertz or something, or sorry, 20 hertz. So it's going to pick up on higher mode shapes as well, is one thing to note, because the tower is made up of obviously a bunch of different modes. It'll also pick up on the fundamental frequency of the shake table itself, because the shake table also vibrates at a certain frequency. So be mindful of that. But what you want to know is like the largest first peak, because the fundamental frequency is going to be as low as possible. So this is a little more rigorous, and we can find multiple mode shapes for more complicated. We can find more mode frequencies for more complicated mode shapes, but the con is obviously it requires a shake table, and there's more, there's more hardware required. There's also this idea of doing a sine sweep. So what you saw in those videos from Professor Kwan is that sine sweep where you'd start off with the relatively low frequency of a sine wave, and then slowly over time you would increase this frequency. And what this does is it means you basically cycle through and see which frequencies the tower is going to resonate at. This is something that we didn't do this year, but definitely should do in future years. And there's also issues with like looking at the data and trying to interpret it. You're also going to get like the frequency of the shake table shaking, and you kind of have to look at those side by side to see what's at your tower and what's not your tower. But definitely is more rigorous than the free vibration shake, especially if you have a complicated tower. Okay. So yeah, those are some things about getting your tower response with the Fourier transform. Now looking into analysis of the ground motion and a little bit about creation of fake ground motions. So a little reminder about response spectrum. So if we go back to this idea of turning a tower into single degree of freedom systems, if we analyze each of those single degree of freedom systems with respect to one ground motion, and what analyzing means is for each point in time that we care about, we'll solve this equation at the bottom here of force is equal to mass times acceleration plus damping times velocity plus stiffness times displacement. So we'll solve that equation for the ground motion for a single degree of freedom system of a certain period. And then we'll find the maximum value for that single degree of freedom system. And then we'll find all of the single degree of freedom systems that we care about, their maximum value. And then once we plot that graph on a graph of period versus displacement, we'll be able to get that response spectrum. You can kind of motivate where this is coming from the Fourier analysis. And so what I've done, and this is going to tie into the next slide as well, is if we look at, so this is ground motion 1 of the previous, of 2019. And you can see our Fourier transform here, and you can see kind of which frequencies make up this ground motion, right? And based on this, you're probably going to notice that this frequency in the response spectrum is going to be heavily impacted. And a great example of this is actually going to come up with ground motion 2 in just 1 second. So yeah, so if you look at the fast Fourier transform of ground motion, you'll see which frequencies it consists of and which you want to avoid, although it's kind of like an indirect response spectrum. And just to reiterate, the response spectrum isn't really a Fourier analysis. It's solving this equation of motion for every single degree of freedom system. It's using kind of a different method, but you'll just see based on which frequencies the ground motion is made of, which ones are going to get impacted the most. And I'll come back to that in just a second when we look at ground motion 2 of last year. But one thing to note is in real life, often engineers and scientists will create ground motions. And sometimes people will be like, seismic design, is that when you make the ground motion? And so this is one case where you can quite literally say yes. And this is done, you can see on the picture on the right, what they'll do is they'll generate Gauss white noise. They'll apply some kind of function to change that noise a little. And then once they do the Fourier transform, they're going to make it match a certain response spectrum, which is the opposite of what we're doing. We get a ground motion and we see what response spectrum we get. And sometimes in industry, they need a ground motion to have a specific response spectrum. And so they'll create a ground motion based on that response spectrum to have that response spectrum. And a lot of times this happens for like tall buildings on the West Coast where there's high seismicity, but because ground motions, we haven't been collecting them for only that long, for like 60 years, but some of these ground motions we think might have a return period of 300 years or 500 years or 1,000 years, we just don't have all the data. And so sometimes we'll create ground motions that are stronger than what we have recorded or have a different frequency content because we think it might be possible for that fault. And in fact, you might be like, wow, synthetic ground motions, that's crazy. I've never seen one. But the truth is that you have, because ground motion 2, this is ground motion 2 of 2019, is synthetic. And the way you can tell is the response spectrum. So if you compare this, the Fourier analysis. So if you compare this Fourier transform to the one for ground motion 1, you can see this one is messy. There's like a couple peaks, but it's, a lot of noise. For this one, for ground motion 2, you can clearly point out which frequencies of SINE were used to build up this ground motion, and then they added some noise to make it kind of not just like a pure sine wave. But you can see like it's a very nice ground motion, and in terms of its shape, it's not as noisy. And this is going to come back to the response spectrum. So if we look at this peak, which happens at 0.167 seconds, and then I've already generated this response spectrum, but this peak is going to be occurring right at 0.167 seconds. That's, you can see in the range, in the relative range, that's the highest acceleration that you're expecting. And same for displacement at 0.167 seconds. You can see it's like it's at a relative high point in the graph. And just an interesting thing that I learned. So here, seismic signal actually decompose, like it solved every single degree freedom system. So if your tower was just a stick with a period of 0.08, this is the full time history, and then it just took the maximum value, if that's either here or here, and then plot it on that graph. And then you can see, for every different frequency, what that graph has looked like. So it's actually solving the time history for that whole degree freedom system and just taking the maximum acceleration or the maximum displacement, just to give you a better sense of how those response spectrums are made. So yeah, hopefully that gave you guys some understanding of how Fourier transforms work, how we use them to understand our tower, how you can use them to kind of understand what's going into a response spectrum and why some frequencies respond differently than others based on what frequencies make up the tower and how they compare to what frequencies the tower, what modal frequencies the tower contains, as well as a little bit about creating ground motions yourselves, which who knows, maybe you'll do one day if you design a really tall building out in like Vancouver or something like that. So thanks. If you have any questions, you can ask them now. And once again, I highly recommend watching that second uncertainty principle video. Gives a little more context into Fourier transforms and their applications. If you have questions, you can either ask them out loud or write them in chat. Yeah, if you have any questions about the Fourier transform, I'm not like a math expert, so I'll try to do my best with what I understand. There's good resources online, but it is kind of like a more complex topic. There's not as much like Fourier transform for dummies stuff out there. That's why I really want to share that video, because it's probably the best one I could find. If no one has any questions, I guess that's it for the Seismic Academy. Thanks so much for listening.